Almost done. We just found the equilibrium quantity of bolts, B star F equal to R over alpha 1 minus C over P alpha K. And we can use this to pin down all the other quantities in the model that interest us. So let's start with the equilibrium fish stuck for the free entry equilibrium. So we had that S star of B star was equal to K 1 minus B star alpha over R. Now we have one version of the model with free entry in which the equilibrium B is this quantity there. So let's just go ahead and substitute this. And we're going to get that the equilibrium stuck of fish if there is free entry. So if B of F will be equal to this quantity there. And what you notice is that there's R over alpha, alpha over R, so we can simplify things very easily. And we find that. So R over alpha cancels with R over alpha, alpha over R. Minus will become minus 1 plus. And so I have, this disappears, so I have 1 minus 1, 0. So this disappears as well. And and K divided by K disappears as well. So I get a very simple expression. This is actually quite surprising. So it looks like, and this, yeah, by the way, this S star of B star F. So let's just go ahead and define this as S star F simply, right? S star of B star F is S star F, just to simplify. So what have we found? Well, we have found that the equilibrium number of fishes in the ocean is a function of the real cost of fishing and the efficiency of fishing. That's it. So does that make sense to you? That as the first day that humans start to fish, then the number of fishes in the ocean is determined purely as function of the industry parameters, the parameters of that industry. No, well, kind of. So what's missing there is that P here is something that's fixed, that doesn't change. But of course, if people start fishing extremely high quantity and there's a very low demand for fishes, then P will decrease because the demand for fishes is not infinite. So in the end, it's not going to be that simple. But here we're looking at again a small economy where the international price for fishes is fixed. Well, it looks like it's fixed. It's a perfectly elastic demand. And in that case, we found a very simple solution that finally it has to be the case that the steady state stock of fish in the ocean is a function purely of the industry. Yes. So and of course, so the higher the cost of fishing, then the higher the stock because there's going to be fewer boats. Higher the price of a fish, then the lower the stock because more boats will want to fish, and better technology, more fishing boat will try to catch fishes as well and will be successful at it. No, so that's for fish stock. Now let's look at total harvest. So we have that the total harvest is defined as alpha BS. So let's do the same exercise as before. So total harvest in the steady state for the free entry fishing is going to be equal to B star of F, S star of F. And then we can just substitute what we know. So this is this quantity here. And S star of F is this quantity here. So it doesn't simplify all that much. I can't do a lot with that. Can basically simplify the alpha there, but otherwise this is what I get. And the solution for harvest looks like the solution for bolts, in the sense that, again, it looks like there is this tension between the same variables. So why? Well, because the better the cost, or the higher the cost, then the less I want to fish. But as at the same time, the less my neighbors want to fish. So there's more fishes to catch. So the better the cost, the higher the cost, or the lower the price, or the lower the technology. Well, it has these double impact on the number of harvests, the amount of harvests. Then what we can do is just make sure that we found out something that was that made sense. What we can verify is that the harvest is equal to the natural growth rate of the fish stock. So we know that the natural fish stock is S star of f equals SC divided by alpha p. So let's just verify what we have just found. So this is equal to, so what I can do is just C divided by alpha p here. So I can just put this SF and then SF, and then put this here. And does that remind you of something? Yeah, it should. So this is the expression for the natural growth rate of the stock of fish without harvesting, and in steady state, in equilibrium. So this has to be equal to harvest, and this is exactly what we find. So harvest with free entry equals to steady state steady state natural growth of fish with free entry. Final question we may ask: what is the total profit of the fishing industry? I let you to think about this for a while. Well, you have to ask yourself is what type of markets do we have? Yes, it's free market. And what happens to free markets, or what happens to markets in perfect competition? Well, profits go to zero. So that's what we use to find the equilibrium. So what's going to happen to the total profits of the firms in the industry? Well, it's just going to be zero. So I can write, it's going to be the total number of fishing boats, B star F, that multiplies the profit of one boat. That's a function of S star F, the steady state stock of fish. And it's simply going to be equal to B star F times 0. So it's going to be equal to 0. So the fishing industry doesn't do any profit in this model, simply because people are going to move in the industry as long as they can have a tiny advantage compared to the alternative. And but then if the profit is negative, then they're going to move out of the industry. The number of fishing boats will decrease and the profit will increase again. So there is no way around it. The fishing industry doesn't have pure profit in this setting. Now let's go back to our important graph at the beginning. So this was the growth of the stock as function of the stock of fish. And what did we know? Well, we knew that the natural growth was tau of st, described by this parabola function. So if you have zero stock, then you don't grow. If you are at natural carrying capacity of the ecosystem K, you don't grow either. Now, though, what's happening is there is fishing. So let's postulate our B star F we just computed, so the equilibrium number of boats in the free fishing industry. So then what is the number of catches of the fishing industry? Well, it's as you can see, it's simply a linear function of the stock of fish. So the more fishes in the ocean, the more catches there is going to be. And so I can just draw this red line here. So the catches is going to be, so the slope is alpha beta star F. And then what is my steady state equilibrium? Well, it used to be K here, but now it's the equilibrium in which the natural growth, tau of ST, is equal to the catches. So every period there would be an increase in the stock of fish, but at the steady state, this natural increase is exactly the number of fishes that are caught by fishermen, such that the stock doesn't change. So at the equilibrium, I have to have that the natural growth minus the harvest equal to 0. So I find that my steady state is here, S star of F. It's lower than K. So that's what's going to happen if people start fishing.